So, okay, last week it was essentially probability theory and theory of stochastic processes. So what we wanted to do was to solve this problem, xt plus xt, and we add a random term. So that was our ODE plus a random term. And this is a random term, basically. And that was the problem last week. So we said that because we have a random term, it's important to specify what is this random term, okay? A precision is that this is not yet SDE, it's just ODE plus a term. And to have SDE, you need to specify this. And we said that generally for this, we use a white nose. I mean, generally researchers use white nose, and the white nose is generally a stochastic process, such that you have that the mean equals 0, the variance is, let's say this is finite, and it's uncorrelated, and you have independent increment. Uncorrelated is fine. So generally to model the random term that you have here, you use a white nose. Now, because it's a stochastic process, let me put maybe, so we know it's a collection of random variable indexed by time. So to specify this, you can use, we said we have generally two stochastic processes. You have discrete continuous time stochastic process. So you have those two stochastic processes. A discrete time that we saw last week, discrete time was the random walk. And we say that just to construct the random walk, which is a basic one, you just need to look at a simple process like this with probability 1/2, probability 1/2. So you take a random variable that gives you -1 with probability 1/2, 1 with probability 1/2, and now you construct something like this. And this is called a random walk. And this random walk, the nice thing is that it has exactly these properties. The mean equals 0, variance equal t, and you have independent increment. So you would like to use, it's a good candidate for this one, but now you have the fact that here we consider that it's continuous, right? It's a continuous process. So, but the nice thing last week also we saw a continuous counterpart of this one. Because if you take the limit of a random walk, you're gonna have a Brownian motion. Okay? So the continuous one is gonna be the Brownian motion, or the Wiener process. So we generally define by WT, right? And this Wiener process has exactly, can be defined as like this. So at 0 it gives you 0. The increment follow a normal 0t minus s, and it has independent increment. Okay? So what we can do then is to use a Wiener process for to specify how random moves. So when we do that, now you have, because this one, you have an heuristic argument actually for this. Let me write that like this. Plus B. I mean, it's a little bit sketchy because, let me write that like that. So basically, now that I specified this, I use my W process, right? Now the question is this thing well defined? And I don't have the time to go, to explain why, but WT generally has a continuous path, so this is good. So the Brownian motion has one property is to have continuous path. But the problem with the Brownian motion is that it's nowhere differentiable. Okay? So it's nowhere differentiable. If it's nowhere differentiable, it means that this doesn't work. Okay? But even if it doesn't work, now we might use only the differential form. Okay? So if you multiply this by dt, you're going to have dxt equal bxt dt plus bxt dw. Okay? And now we can see that this is just wt plus 1 minus wt. And this is just an increment. And we know that this increment follows this normal distribution. So this is fine because this one is just a normal distribution, right? So we have a random term with a normally distributed. You have independent increment. So this works. So, and this one gonna be what you're gonna call xc. Okay? So basically, we started with this, and we specified this using the differential instead of the derivative of the Brownian that which is not defined. Okay? So now that we have the SDE, we would like to find a solution of this. So a solution, if you just integrate that, what do you have? You have, if you use the integral from 0 to t of this is going to give you what? Xt minus x0, right? And you're going to have 0 to t dx0 dx plus 0 to t dx s dws. Okay? So you have your SDE. If you just take the integral, like a usual ODE, this one going to give you this, which is fine, you know your initial condition. This one is just a time derivative, the time integral, like a Riemann integral. Now you have a new term, and this one is actually a stochastic integral. Okay. So what we would like to do now, the entire point is to go from SDE to the process, or from the process to the SD, the dynamic given by the SD. Okay? But to do that, the first thing we can do is to look at the integral and look at this new element that we have here. How can we define this integral, right? So we have to look at stochastic integrals. And generally the form, let me put ST SW Okay. So one thing with this stochastic integral is that not only that this thing is random, right? So this entire thing is random. So it has a mean and a variance. So that's a random variable, basically. Okay. So now we would like to understand this, and one way to understand that is to use the basic integration theory. So you just start with take a step function. I took an interval s to t, like so you're gonna have an interval s to t, right? You're gonna take a partition, right? So one thing you can do, if you start with a step function, you can define this step function greater than 0. I'm gonna have some coefficient, and I'm gonna define that g plus 1, gd minus n t. So I define a step function that take this value on each small interval here, right? If I have that, I just look at what I'm going to have, what type of integral I can have with this. dw, that, and this, like in major theory, I'm going to give you gw. Now, this is 1 in this interval, right? So if you put your Brownian motion on this, it's just going to give you btg plus 1 minus btg. Yes. Okay. So basically, you have the increment of your Brownian motion, and at each increment, you have this value. So that is exactly what your step function gives you, the integration of your step function, right? So now, you can use the usual approximation procedure. You use that step function, you go to simple function, and now you have simple function that can converge to your function f. And now you can write that as a limit, the limit when n goes to infinity of, becomes a summation ft and t greater than 0 t, so it's w, and now you have the tg plus 1 w tg w. Okay? So your stochastic integral is just your usual Riemann sums. Okay? This is one definition of the stochastic integral. So it's exactly like the Riemann integral, but this time you have a Brownian motion here. And we're going to see that for the Riemann integral, this term doesn't really matter because your Tg for Riemann integral, the Tg should be between Tg and Tg plus 1, right? So basically when you take, you have Tg, you have Tg plus 1, and it doesn't matter which term you're going to take here, right? But now, for a stochastic integral, do you mind if I erase that? For the stochastic integral, the choice of Tg star is really important. And one quick example is that if you take a quick example, is that if you take, if I take in this case my w, my f, because my f is like it's a class of function of stochastic processes because it depends on w also. So it's a stochastic process. So what I can do, I can take a basic stochastic process and see if it has exactly the same mean or variance, if I have at the end the same random variable. So one case is that, okay, let's say that your f, Sw, is just your simple Brownian motion. Okay? If I have that, my stochastic integral, and now I'm going to take a term, I'm going to take the leftmost term, right? And substitute that here. So if I have this, it's going to be equal to G0. I have this. Now my Tg star is equal to the leftmost point, W, Tg plus 1, Tg, right? And I take another one, here. And this time I take, let's say, the rightmost point. Okay. So normally, if it was a Riemann integral, it doesn't really matter, right? But in this case, what you're gonna have is that if I'm looking at the expectation of the first one, T1, T W. If you look at the expectation of this, you take the expectation, right? If you put the expectation inside, because it's linear, what's going to happen? What is this term? This term gives you, imagine you have your TG here, TG plus 1, right? The first part gives you the Brownian motion here, right? The second part gives you the Brownian motion between TG and TG plus 1. So between TG and TG plus 1, okay? So if you take the expectation, you have kind of the covariance. And the thing is that, what did you say about the Brownian motion? It has independent increment. So this thing will be equal to 0, okay? Now, if you take for the second one, what's going to happen? If you take the expectation of this, you can rearrange that. You have a TG plus 1, you can add and remove WTG, right? So you're going to have TG plus 1 minus TG squared plus WTG plus 1 minus WTG. So you have this expectation. Okay? This one again is exactly the one we had for here. We did that exactly the same problem. Those are two independent increments, 0, right? And this one is what is the square of the variance of an increment, which is like this equal to t. It's like having TG plus 1 minus TG. So this is going to give you, let's say, TG plus 1 minus TG. Okay? So just by taking the term at TG and the term at TG plus 1, you have two random variables, two different random variables, right? So to continue, you need then to make a choice, because you can generalize this, you can take a point anywhere here. And you have a general case where you can write your TG star is equal to 1 minus lambda, your TG, and your lambda TG plus 1. And if you take, so TG star equals TG when lambda equals 0, right? This, it means that each time you're going to take the leftmost point, and this is going to give you an Ito, what is called an Ito integral. Okay? If you take TG star to be the midpoint, so it means that lambda equals 1/2, you have what is called a Stochastic integral. Okay. And after that, you can take lambda to be anywhere between TG and TG plus 1. The thing is that this, if you do that, you're going to have a different type of integral. And because you don't know what's going to happen in the future, so you're limited by the information that you have at time TG.